Did you know that concrete is reflective when it's wet? Well, yeah, you probably did. But what you might not know is that it plays havoc with radar deployments, and it's a result of a phenomenon that we refer to here as benching. But to explain all this, I'll tell you some secrets about radars. So for starters, it's all about the basic physics of how radars work. Now, I've got a very scientific prop, which is a torch, and radars look at their target subject similarly to this torch. It has a focused area of light in the center, and then around the edges, it starts to get a little bit dimmer, and that's very similar to radar, so keep that in mind. So radar manufacturers will look at this pattern of light and they'll assess this and define it as their beam angle. So where their radar is positioned above the target subject, their radiation pattern is, for instance, 8 degrees. But what they don't typically tell you is that outside of this beam angle, you're still getting signal. And what's actually occurring is that in your 8 degrees beam angle, you're getting your strongest point out to 50% strength. But what happens outside of this 8 degrees is that you actually have additional signal coming out the sides between 50% to about 10% strength. Now, with most of our strongest signals coming back in this 8-degree channel and some smart filtering that's applied to most radars across all manufacturers, we can typically cover most use cases and most scenarios to accurately record the distance of our target subject. But why am I even talking to you about this, and what does it have to do with wet concrete? So to show you why it's important, I'm probably just going to have a crack at replaying a bit of a real-world scenario where we install our radar in a sewer riser, and there's a lot of concrete and a lot of water and a lot of obstructions that we have to deal with. So here's our sewer riser. We've got a column of concrete and then water passing through at the bottom. And then we've got concrete either side, and the water goes in here. Now, we would typically mount our radar up the top here, and we would have our 8-degree radiation pattern targeting a subject here, and that's our water. Now, we've also got those stray signals coming out the side, which are typically weaker and typically ignored. But what happens when the water level rises all the way up because of a blockage or an obstruction and the whole sewer is wet? Well, we're going to accurately measure the depth of the water here. But once it recedes, all of this concrete is going to be wet and super reflective like a mirror. Now, what that means is that when we're looking at our recorded data, we've got height over time. And what we'll see is that the water level would have come up, and then if this is our expected level here in that gully of the riser, we're never actually going to see it. It's going to flatline because of that reflective concrete, even though it isn't our intended target subject. And it will only be when that concrete dries out and becomes less reflective that we'll begin to see our typical trend within that gully. And as you can see from the data, we do actually get something that looks a bit like a bench, which is caused by that concrete bench. So to make this really clear, I'm going to do a side-on view. So our radar would be mounted up the top here, and then at the bottom we've got that concrete bench, the gully where our water flows in here. And this section here where we see that benching is actually because we're getting those stray beam angles, even though they're much weaker, reflecting back off this surface as if they were our intended target subject. So in our data, it's really represented as this static bench of data. Now, I wish I could control this and stop that concrete from getting wet, but I can't. What we can control though, is what we do with our radar. And we can apply some smarts, which basically means we can tell our radar to just block out this section, and any reflections that occur here are completely ignored, which means that when we're looking at that same trend of data, instead of being static on that bench, it would just skip past it and then keep going down. The really cool part though, is that we know that we're not just going to see concrete benching in a well. We might see rungs of a ladder. We might see a pipe entering the sidewall. And what we can actually do is apply a mask that skips over these as well to ensure that the whole time we're monitoring our target subject, which is the height of the water, we're getting completely accurate and true measurements of exactly where that water level is, despite multiple obstructions in your riser. So if you do have any more questions about this or how we solve for complex problems like this, please head to our website and contact us.